Hi everybody, we're going to start talking about buffers today. So let's talk about the definition of a buffer. A buffer is a solution that resists or opposes a change in pH when you add extra H pluses or OH minuses. So if you were to take distilled water, for example, and add a drop of 10th molar HCl, the pH will drop significantly. Or if you take distilled water, add a drop of NaOH, the pH will increase significantly because the concentration of the H plus or the OH minus has changed, and so your pH will change. A buffered solution is a solution that when you add H pluses or OH minuses to it, reacts with them, so it eliminates any extra or excess H pluses or OH minuses that you're adding, and so the pH remains about the same because your H plus or OH minus concentration remains about the same. A buffer is made up of two components. So a buffer is a weak acid with its salt or its conjugate, or it could be a weak base with its salt or conjugate. So a weak acid and its conjugate, or a weak base and its conjugate. So each buffer has to be made up of two different things together. One of them is acidic and one of them is basic. So we had just been talking about common ion effect, and the reason why we were talking about common ion effects is because when you have a common ion effect like that, you basically have a buffer. So if you have HF, which is a weak acid, and F minus, which is its conjugate, if you take HF, combine it with F minus, you've made a buffer. The acidic component of that buffer is the HF, the basic component of that buffer is the F minus. Or if you take ammonia and ammonium, so ammonia is a weak base, its conjugate is NH4 plus. And so if you combine them together, you've made a buffer, and it's a basic buffer. This is the basic portion of the buffer. This is the acidic portion of the buffer. As you can see, a buffer is made up of a weak acid and its conjugate, or a weak base and its conjugate. And so a buffer does not hold the pH at 7. It holds the pH, but not necessarily at 7. So an acidic buffer will hold the pH at a low pH, like, if it's HF or something, and F minus, it probably would hold it at 2 or 3. A basic buffer will hold it at a basic pH, so maybe 9 or 10 or something like that, depending on what the buffer is. The way that it works is that each buffer has an acidic and a basic component to it, and so let's look at HF and F minus, for example. So we have HF and F minus. This is the acidic portion of this buffer. This is the basic portion because that's a weak acid and its conjugate base, right? Let's say I add some H pluses to my buffer. Well, H plus is an acid, so which part of this buffer will react with it? Well, the acid will react with the base. So you're going to react with the F minus, and you're going to form HF. So when you add H pluses to this, basically you use some of the F minuses to form some more HF, and as long as you still have some HF and some F minus, you basically have the same species in solution, just slightly different concentrations, and so your pH remains the same. What if I add hydroxide ions to this buffer? Well, hydroxide is a base, so it would react with the acidic portion. So if it reacts with HF, you would form water and F minus. And so basically you use up the OH minuses completely, you use up a little bit of the HF and form some more of the F minus. So at the end of your reaction, you still have HF and F minus, same species, just slightly different concentrations, and so the pH will be about the same. So by eliminating any excess H pluses or OH minuses, you've kept the H pluses or OH minus concentration the same, which means the pH is the same. Let's look at a basic buffer. So NH3 is a weak base, and NH4 plus is its conjugate acid. So let's say I take some acid and add it to this buffer. Which part of the buffer would react with it? Well, H plus is an acid, so it's going to react with the base. And guess what it's going to form? Well, it's going to form NH4 plus. So if I only add a little bit of H pluses, I'm going to use that up. I'd use up a little bit of the NH3, but I'd still have some. and I'd form more of the NH4 plus. So I still have the same species, and so same pH. Let's see if you add hydroxides, which part of the buffer would react with it? Well, hydroxide is a base, so it's going to react with the acid. And it's going to form water. And then NH3. So again, we've eliminated any extra H pluses or OH minuses, and we end up with leftover NH4 plus, a little bit more of the NH3, and so you have the same species, so the same pH. At some point, if you add enough H pluses or OH minuses that you use up all of this or all of this, then you don't have a buffer anymore. But as long as you have some of this, of the buffer components left over, it would still keep the pH about the same. So let's look at how you can calculate the pH of a buffer and what happens when you add an acid or a base to it. So we have a buffer here. It is 1 liter of acetic acid and sodium acetate, where the acetic acid concentration is 0.70 molar and the sodium acetate concentration is 0.60 molar. So we want to calculate the pH for that. And so we did that basically last time when we talked about common ion effects. So I'm going to start with my salt. I'm going to write the dissociation for that. So this is a soluble salt, dissociates completely into sodium ion and acetate ion. Then I'm going to write the dissociation of my acid, my weak acid. Because that's a weak acid, it partially dissociates into H plus and acetate ion. And so the acetate ion, basically, that's my common ion, where I get common ion effect. So if I want to find the pH for this, what I could do is I could do an ice chart. And for my acetic acid, my concentration is given to me as 0.700 molar. I don't have any H pluses to start with. I do have some acetate to start with from the sodium acetate. This is coming from the sodium acetate. My sodium acetate is 0.60 molar. I use up some of this, so minus X. I form some of this plus X, 0.7 minus X, X, and 0.6 plus X. So then I write my K expression for my acid. It is the concentration of the H plus times the acetate ion over the acetic acid. And so that is equal to X times 0.6 plus X over 0.7 minus X. And my Ka for acetic acid is 1.8 times 10 to the negative fifth. If I solve for X, that's going to be my H plus concentration at equilibrium. It is 2.1 times 10 to the negative fifth, and so my pH is negative log of that, which is 4.68. So basically it's an ice chart for my weak acid, or if it's a basic buffer, it would be an ice chart for your weak base. But the only difference is the initial concentration of your conjugate, you're going to get that from your salt, because it has that conjugate in it. Okay, well, what if I take a milliliter of 1 molar HCl and add it to that buffer? That should say in part A here. What happens to the pH? How do I calculate the pH? So what you do here is, if you're adding an acid or a base to your buffer, you want to first figure out what reacts with your acid or your base that you're adding. So my buffer solution is made up of acetic acid, that's the acidic portion, and my acetate ion, which is the basic portion. So if I add some HCl, which is basically extra H pluses, which one would react with it? The H plus would react with the acetate, right? So first you want to write out a reaction for what happens. So you're going to write H plus, this is coming from the HCl, plus the acetate ion from the buffer is going to react together. Acid-base reactions usually go to completion or very near completion. So when you write an acid-base reaction, you write one arrow, one single arrow. It goes to completion. Versus if you're writing the dissociation of the acid, a weak acid or a weak base, that is an equilibrium. So look at the difference between them here. This is a weak acid dissociating, partially ionizing, so it's an equilibrium. This is an acid, HCl, reacting with a base, which is the acetate portion here. So that would be one single arrow. The product is going to be CH3COH. Okay, and what we're going to do is we're going to do a BCA table. Sometimes they call it RBCA table, reaction before, change, and after. It's a little bit different from an ice chart. So this is an ice chart. Sometimes they call it a rice chart. Reaction, initial, change, equilibrium. This is an equilibrium, meaning it goes back and forth. Versus this BCA table or RBCA table is for one-way reactions, reactions that go to completion. So that's the difference between them here. Usually rice charts you do in terms of molarity. Usually BCA tables you do in terms of moles. That's not a rule, but that's usually what we use. Sometimes we call these Rebecca charts. My former students have named them Rebecca, and so I have a mole, little stuffed animal mole in the classroom, and we've named her Rebecca after BCA tables because we usually do the BCA tables in moles. Anyway, so this is before the reaction starts, the change, and then after the reaction is done. Again, we do before and after because this is a reaction that goes to completion, it's done. Versus here we do equilibrium because the reaction is really never done. It's in equilibrium, so particles are moving all the time, changing all the time, but the rates are equal to each other. So that's the difference between them. So when you are reacting an acid and a base, you do a Rebecca chart or a BCA table, whichever you want to call it, and you want to do this in moles. So you want, before the reaction, initially, how many moles of H plus do I have? How many moles of acid do I have? So I have 1 milliliter of 1 molar. So this is 0.001 liters times 1 mole per liter. So that gives you 0.001 moles. So that's what I'm going to put here, 0.001 moles. My acetate, before I start, I know that I have 0.60 molar and I have a liter of it. So 1 liter times 0.60 moles per liter. So that's going to give you 0.60 moles. Right? So that's my acetate, 0.60 moles. How about my acetic acid? So I actually have some acetic acid sitting here in my beaker, right? So the concentration of the acetic acid is 0.70 molar and I have a liter of it. So I have 0.70 moles of this. Okay, with BCA tables, you don't do the X's and all that stuff. You have a limiting reactant and an excess reactant. So let's look at our reactants here. This one, they're a 1-to-1 ratio, and this one I have 0.001 moles, and this one I have 0.60 moles. So which one's my limiting reactant? My limiting reactant is this one, right? I have less of it, and it's a 1-to-1 ratio. And so that's what's going to be used up. So I'm going to use up, because this is my limiting reactant, I'm going to use up the 0.001 moles. And because this is a 1-to-1 ratio, I'm also going to use up out of this one 0.001 moles. And this is a product, so I'm going to form 0.001 moles, again, because it's all a 1-to-1 ratio. So after the reaction is done, I would have none of that H pluses, and that's why your pH should remain the same, because we've used up all those H pluses. This is going to be 0.599 moles, and this one's going to be 0.701 moles. So after I've added my acid, I still have my buffer left over, right? I have acetic acid and my acetate, and I don't have any H pluses. My concentrations are slightly different, but they're pretty close, and so my pH should remain about the same. So once you've done your Rebecca chart or your BCA table to figure out the moles of what you have and what you're, after the reaction, what you're left with, then we look at what we're left with and we try to figure out the pH of that. So what are we left with? We're still left with the buffer, acetic acid, which is the weak acid, and its conjugate. So to do it, we are going to do an ice chart for the dissociation of the weak acid, just like we did here. We're just going to use the new molarities. And since we did the Rebecca chart with moles, we want to divide by the total volume just to get the molarity here. So I had a liter and I added 1 milliliter of HCl to it, so my total volume is 1.001 liters. And so this gives me 0.598 molar. This gives me 0.7003 molar. We can round to 6 at the very end. So now, again, I'm left with a buffer, a weak acid and its conjugate. I want to find the pH for that, so I'm going to do an ice chart for the dissociation of my weak acids. So CH3COOH partially dissociates into H plus and CH3CO minus. We'll do an ice chart because that's an equilibrium. What I'm left with for the acetic acid is 0.7003 molar. This is 0, and this is 0.598 molar. Some of this gets used up, some of this forms. 0.7003 molar, X, and 0.598 plus X. My K expression is the concentration of the H plus times the concentration of the the acetate ion over the acetic acid. 1.8 times 10 to the -5 is equal to X times 0.598 plus X over 0.7003 minus X. X is my H plus concentration at equilibrium. In this case, it ends up being 2.11 times 10 to the -5. Take the negative log of that. My pH is 4.68. Look at that. My pH did not change. It's 4.68 before. It's now 4.68. So even though we added a whole milliliter of 1 molar HCl, it got used up. That extra H pluses got used up, and I still have my buffer left over, and so my pH is pretty much the same. Now, there is an easier way to calculate the pH of a buffer, and it's called the Henderson-Hasselbach Equation, and it's written right here. We can derive it if you want, but you know, you can come see me and I can help you derive it if you'd like, but this is the equation for it. You can just use it. And so this can be used if you have a buffer, meaning a weak acid and its conjugate or a weak base and its conjugate. Both have to be there, so it has to be a buffer. And so if I'm calculating this right here, the pH of just my buffer, I could use the Henderson-Hasselbach. So pH would be equal to pKa, so negative, P means negative log, right? So negative log of the Ka value, plus log of the conjugate base, so the acetate ion, over the acid, which is the acetic acid. So if I were doing this here, I'd do pH is equal to negative log of my Ka value, which is this right here, plus log of my acetate ion concentration, which is 0.60 molar, divided by the acetic acid, which is 0.70 molar, and that's it. No need for an ice chart. So you could do an ice chart, or you could do the Henderson-Hasselbach. If I was adding the acid to my buffer, I'd still have to do my Rebecca chart. So I have to do this step, but then once I'm done with the step and I know the concentration of my acetic acid and my acetate, I can plug it into the Henderson-Hasselbach right here with these values. So it is your choice whether you want to use Henderson-Hasselbach or an ice chart. Probably the Henderson-Hasselbach is just a little bit shorter. You use this equation if you are doing an acidic buffer like acetic acid with acetate. You use this equation, which is pretty much the same, everything is flipped though, for a basic buffer. So if I have ammonia with ammonium ion, then that's when I would use this one. So this one would solve for the POH, you'd use Kb, and these are flipped conjugate acid over base as opposed to base over acid. P again just means negative log. So pKa means negative log of Ka, pKb means negative log of the Kb. The pH of a buffer is controlled by the strength of the acid, pKa, or of the base, the pKb. So, something like acetic acid buffer, its pH is 4.68 if it's that concentration because of the Ka of your acid. So the higher the Ka value, the lower the pH, of course. So what the pH is of a buffer that it's going to hold that pH at is controlled by your Ka if it's a weak acid conjugate base, or by your Kb if it's a weak base conjugate acid. When the conjugate acid concentration is equal to the base concentration, or when the conjugate base is equal to the acid concentration, then the pH is equal to pKa. So what we're saying is if this number is equal to this number, so if they're both like 1 molar, then that becomes 1, log of 1 is 0, so pH is equal to the pKa. If it's a basic buffer, if these two are equal to each other, then again, this fraction is equal to 1, so log of 1 is 0, so the POH would equal to the pKb in that case. Each buffer has a buffering capacity, and so the buffering capacity is basically how much acid or base can I add to my pH before I see an appreciable or a meaningful change in pH. And a meaningful change in pH is usually a change in pH of 1 unit of pH. So it goes like from 4 to 5 or something like that. Each buffer, again, has a different buffering capacity, and it has to do with the concentration of the buffer. So if I have a buffer, for example, that is 5 molar of each of the components versus 0.05 molar of each of the components, then the 5 molar one would have a higher buffering capacity. The reason for that is you can add more H pluses or OH minuses before you run out of the component of the buffer that it's reacting with. And so you can keep adding more and more and more, and you're not going to run out of the two components, and that way you still have your buffer, so it keeps buffering. Once you run out of one of these components, again, then your pH will shoot up or shoot down, because you don't anymore have a buffer, you just have one component. So in our next lesson, we are going to practice some more calculations with buffers, and we're going to do this problem.